Alright, hello everyone. I hope all of you are doing great. So today we'll be discussing the solutions to Codeforces round 813. This round just ended like an hour ago. It was 2 hours 15 minutes long, and it was a pretty nice round, I think. The only thing that's problematic here is that there was a very less difficulty gap between B and C, and there was a very large difficulty gap between C and D. So I think if problem C would have been a little bit more harder, then I think this problem set would have been very ideal. But nevertheless, it's not a bad contest at all. So I really enjoyed solving the fourth problem, and I think the problems after the fourth one are also really interesting. So you should definitely try them out. But I will only be discussing the first 4 problems today, which are the ones that I was able to solve during the round. So yeah, without any further ado, let's start with the solution to problem A. Cool. So this is a really simple problem. So we have a permutation of length n and also an integer k, which is less than or equal to n. And we can perform operations obviously, and in one operation we can choose 2 indices I and j, and we can pretty much swap pi with pj, right? So in an operation you can swap 2 elements. So what we have to find is the minimum number of operations that are needed to make the sum of the first k elements as small as possible, right? So yeah, this is the problem. So the solution here is pretty simple. I don't think anyone here would not have solved this problem, but still, let's, for the sake of completeness, just quickly discuss it. So for the sum p1 plus p2 up till pk to be minimum, all elements in the range from 1 to k should be in the prefix of length k, right? So this is an obvious condition because that is the only condition where the sum will be minimum, right? The sum will be 1 plus 2 plus 3 up till k, and this is the minimum sum that we can get, obviously. So the solution here is pretty simple. What we have to do is, for any element, so for any element which is less than or equal to k and is not in the prefix, we will need to swap it with some element in the prefix, right? So that element now comes into the prefix. So the answer is basically nothing but the count of all the elements. So the count of such elements. So yeah, that's going to be our answer, because for any element which is in the suffix of k plus 1 to n and that is smaller than or equal to k, we have to swap it with some element in the prefix, and we can't avoid that, right, since we want all these elements in the prefix. So that's why this is simply going to be the answer, and this can be pretty much easily calculated. So this was problem A. So the code here is again pretty simple. What we do is we simply iterate from k plus 1 to n, and if we find a number which is less than or equal to k, we increment our answer. So yeah, that's pretty much it for the first problem. Let's now move on to problem B. Cool. So this is again a pretty simple problem. So here we have been provided with an integer n, and this is a constructive problem. So basically what we have to do is, yeah, we have to find the permutation of length n such that this sum is maximized. So the sum is basically LCM of 1 p1 plus LCM of 2 p2 and so on. So we have to maximize the sum of LCM I pi over all I, and we have to build a permutation of all the elements from 1 to n. So yeah, that's pretty much what we have to do. Let's have a look at the solution now. Okay, so the solution basically is pretty simple. So it's based on one main observation. So the main observation required to solve this problem is that the LCM of I and I minus 1 is always I into I minus 1. Or in other words, I and I minus 1 are always coprime, right? So this is a very well known and easy to prove fact that I and I minus 1 will always be coprime, and that's because any number which is divisible by I minus 1 can never be divisible by I. So that is why they can never have any common factors, right? So yeah, that means the LCM of I and I minus 1 will always be equal to I into I minus 1. So what we can do is we can simply iterate in reverse order. So we can iterate in reverse order. So let's see what will happen. So what will happen is that let's say we are currently on n. So this is, let's say this is n, and let's say this is, yeah. So these are the last two indices on which we are on, right? So what happens is that if we just consider this as the n minus 1th index and consider this as the nth index, what happens is that the maximum value of the product for this is n into n minus 1. And similarly, the maximum value of the product of I into P of I, LCM of I and P of I, is nothing but n into n minus 1, right? So these are the values of the maximum. So these are basically the maximum value of I into LCM of I for I is equal to n and for I is equals to n minus 1. I'm sorry, these are the maximum value of LCM of I comma P of I for I is equal to n and for I is equal to n minus 1. And it so happens that these maximum values can be achieved, and they can be achieved if I put n at index n minus 1 and if I put n minus 1 at index n. So this is pretty much doing our job. So if we do this, then we are basically reaching these maximum values. So that means we can just greedily keep doing this, right? So we can greedily keep doing this in reverse order. So for each I, what we'll do is we'll assign ai is equal to I minus 1 and ai minus 1 is equal to I, right? So yeah, that pretty much completes the solution. Let's just have a look at the code. So what we are doing is we are going in reverse order, or we can also go in forward order. It doesn't matter depending on whether n is even or odd. So we are simply assigning ai to I plus 1 and ai plus 1 to I, and that's it, right? The proof is again trivial, that these are the maximum values that we can get for any index, and these maximum upper bounds are just achievable, right? So yeah, this is the solution to problem B. Okay, now let's move on to the third problem. Cool. Again, this problem is a bit on the easier side. It's not like a general Div-2 C, which are generally a bit more harder than this, but nevertheless. So what we have here is we have an array of n positive integers, and in one operation what we can do is we have to choose all the occurrences of a number x, and we have to convert ai is equal to 0 for all of these occurrences, right? So we will just pick a number and then we will choose all of its occurrences and convert them to zeros. That's what we can do in an operation. What we have to find is we have to find the minimum number of operations which are required to sort the array in non-decreasing order. Yeah, so the problem is pretty easy to understand. So yeah, let's just have a look at the solution now. So the solution is again not very hard. So it builds upon again one basic observation, and that observation is that basically if we are doing an operation on the ith element, then we are converting it to 0, right? And if the ith element is 0 and we want the array to be sorted, then all elements which are before it should also be 0, right? So if we perform operation on the ith element, on the ith position, then all elements in 1 to I basically should be 0. Yeah, so this is obvious, because if we perform the operation on the ith element, then ai will become 0, and if the array has to be sorted, then all elements in 1 to I minus 1 should also be 0, right? So that means the final state of the array would be some prefix made up of zeros and then some other suffix which is sorted, right? So the final state of the array would be a prefix of zeros. So this prefix may be empty. That means there are no zeros if the array is already sorted, and then some elements, some non-zero elements in sorted order, right? So this is how the array is going to look like. So I can also draw how it looks like. So it's basically looking something like this. There will be some zeros, and then there will be some sorted array, right? So this might not be linear because some elements might be equal, but it should be sorted in non-decreasing order, right? So this is how the array has to look like. So what we are interested in, we are interested in this sorry, what we are interested in is this particular index where we will find the last 0, right? Cool. So yeah, so the final state will look something like this. So there will be zeros in 1 say I, so all elements in 1 to I will be 0 for some I in this range from 0 to n. I can also be 0, that means there are no zeros to start with, and then some sorted array, right? So what we have to find is, we just have to find the minimum value of I such that this condition can hold true. So we need to find the minimum possible value of I, and basically then convert all the elements in 1 to I to 0. So, and then convert all elements in 1 to I to 0. And the number of operations will just be the number of unique elements in 1 to I, because in one operation we are taking all the occurrences of an element. But the problem here is that we can't just arbitrarily choose an I. So there are two conditions that an index I needs to satisfy. So there are two conditions. So the first condition is that the array from I plus 1 to n should be sorted, right? So if we are iterating on this I to, we are claiming that I is the last occurrence of 0, then that means all the elements in I plus 1 to n should be sorted, right? So this is the first condition. Cool. Now the second condition is something which is a bit tricky. So the second condition is that if there is an element which occurs in the prefix in 1 to I and also in the suffix, then it is not allowed, right? So then the value I is invalid. So I should satisfy the condition that there should be no element which is in the prefix as well as in the suffix. So what I mean here is, in the prefix originally, finally it would be 0, but originally if there is an element which is also in 1 to I and which is also in I plus 1 to n, then that's not allowed. And the reason for it is pretty simple to understand. That's because if we do an operation on that element, then its occurrence in the right half, that means its occurrence in the suffix, would also become 0, and that is not allowed, right? So yeah, pretty easy to understand. So that's why these are the only two conditions that an I needs to satisfy. So we just find the smallest I which satisfies these two conditions. Then answer will be the number of unique elements in 1 to I, right? Yeah, so this is it. Cool. So yeah, this completes the solution to problem C. Let's just have a look at the code. So the code again is pretty small. So what we do is, first of all, we make an is sorted array which denotes whether the suffix from I to n is sorted or not. It's pretty easy to understand. If I plus 1 is sorted and ai is less than equal to ai plus 1, then I is also sorted, right? So is sorted of I will be true. So this is pretty trivial. Then what we do is, we go for all the indices from 0 to n, and basically what we have to check is, first condition is that is sorted of I plus 1 should be true, and the second condition is that there should be no element whose one occurrence is also in I plus 1 to n. So to tackle that, what we do is, we store the rightmost occurrence of each element, and then we calculate the maximum rightmost occurrence of all the elements in the prefix, and if that maximum is greater than I, then obviously our condition gets false. So this maximum should be less than equal to I, and is sorted of I plus 1 should be true. If that's the case, then answer would just be the number of unique elements in 1 to I, which I am putting in a set, so it will just be the size of the set, and then we'll break out because we have found the smallest value, right? So yeah, this completes the solution to problem C. Let's now have a look at problem D, which is really interesting and a pretty hard problem, I would say. If I would get the chance to rate this problem, I would say this is around 2000 level problem at least, right? Yeah, cool. So let's see what this problem is saying. So we have an array of n positive integers yet again, and we also have an integer k which is less than or equal to n. So what we can do is we can apply the following operation at most k times, and an operation basically denotes choosing an index and changing the element at that index to any value in the range from 1 to 10 raised to the power 9. So we can choose any index and change it to any value that we want, right? And once we apply all these k operations, what we'll do is we'll build a complete undirected weighted graph with n vertices from 1 to n. So there is an edge between each pair of vertices. That's what a complete graph means. And the weight between the edge from L to R is going to be the minimum element in the range from L to R in the array that we have after performing all the operations. So the weight of the edge from L to R would be the minimum element from AL to AR. Right. Yeah. So what we have to do now is we have to find the maximum possible diameter of the resulting graph after performing these k operations. Right. So the diameter of a graph is basically the maximum value of the shortest part between any two pair of vertices, right? So basically if we iterate on every pair of vertices and we find the shortest path between them and then we take the maximum value out of that, then that will be the diameter of our graph, right? Yeah, that's it. So this is the problem. Not very hard to understand, but yeah, this diameter term can be a bit tricky, I admit. But anyways, let's have a look at the solution now. Cool. So the solution will be based on a few observations. So let's start with the first observation. So the first observation is pretty simple. So this is a trivial observation, that is that if we change any element, we will convert it to 10 raised to the power 9. So we will convert any element only to 10 raised to the power 9. Now I don't even think I need to prove it. Well, it's pretty obvious that we need to maximize the diameter, and obviously if the elements are as high as possible, it can't hurt us. So if we are changing something, it makes sense to change it to 10 raised to the power 9 only, right? Yeah, that's fun thing. Cool. Now let's look at the second observation, and this is the most important observation of this problem. Yeah. Okay. Yeah, so this observation basically defines the diameter. So what will be the diameter of the graph? So this basically answers the problem, how will the diameter look like? Yeah, that's the better way to represent it. How will a diameter look like? So what I am claiming is, I am claiming that for any two vertices I and j, the shortest path will never consist of more than two edges. So the shortest path will never take more than two edges, and the reason for that is if we are taking two edges, then we can just go from I to the minimum element and then to the minimum element to j. So we can go from I to the min element. Let's say mn is the min element, and then we can go to j. So we start from ai, then we go to the minimum element, and the cost of this is mn, and then from mn we go to aj. So the entire cost will be equal to 2 into minimum element, right? And obviously if we are taking more than two edges, then the cost of any edge would be greater than or equal to the minimum element, right? So if we are taking 3 edges, then the minimum cost that we can have is 3 into mn, and 2 into mn is strictly better than that. So that means we will never take more than two edges, right? So with this we can write down the second observation, and the second observation is that the so what the diameter will be looking like, right? So the diameter is nothing but the maximum value among all these shortest paths, right? Yeah, so what will happen is that we will find, yeah, so between any two nodes there is a direct edge. That is one possibility, and we can go to the minimum element and then we can go to the second element, and that's the second possibility, right? So for any two nodes for any two nodes I and j, the length of the shortest path is nothing but minimum of 2 into mn, and the length of the direct edge between I and j, which is nothing but, so yeah, direct edge between I and j. Yeah, so this is the length of the shortest path, and diameter is nothing but the maximum among all these values. So diameter is equals to max of min of whatever I have written above, right? So diameter is nothing but max of these values. So in other words, what I can say is that diameter is nothing but max of, so diameter is nothing but the minimum value of 2 into mn and the max weight edge of the graph. Yeah, again easy to understand, because for any two vertices the length of the shortest path would either be 2 into mn or it would be the weight of the direct edge between them. So if we want the maximum value of all these shortest paths, then that would either be 2 into mn or the max weight edge of the graph, whatever is minimum. Because if all the edges in the graph are smaller than 2 into mn, then the diameter becomes the max edge of the graph, and if there is some edge which is greater than 2 into mn, then the diameter becomes 2 into mn, right? So yeah, this is the important observation, that the diameter will be nothing but 2 into minimum element of the graph. Yeah, so that's it. This is the second observation. Yeah, but the problem is not yet solved. Let's have a look at the third observation. So the third observation is that the edge weights decrease with the distance, right? So for any I, the edge weights from I to j increase as j increases or decreases, right? And the reason for that is that the edge weight between I to j is nothing but the minimum element in I to j. And if the range increases, then the minimum element obviously decreases, right? So that means the max weight edge will be between a pair of adjacent nodes, that is I and I plus 1. So we only need to check adjacent edges. We don't need to check all the O of n square edges. We only need to check adjacent edges, and the max weight edge will be nothing but the maximum weight edge between all the neighbors, right? So that's what we are interested in. Cool. Yeah. So now we can change the definition of a diameter. It's nothing but 2 into mn. So diameter is nothing but minimum of 2 into mn and max weight edge among all the neighbors, right? Cool. Yeah, makes sense. Now what we can do is basically we can iterate on this max weight edge. This is the idea. We can iterate on this max weight edge among all the neighbors, and then we can try to find out the maximum possible value of the minimum element for that particular edge weight, and that way we will be able to find the maximum possible diameter, right? So let's try to understand. Well, this is not the spelling of neighbors. Let me just confirm. Yeah, N-E-I-G-H-B-O-U-R. I don't know why it says that this is the wrong spelling, but doesn't matter. Yeah, cool. So yeah, the final idea. I know this problem is a little bit involved, but I think I'm trying my best to understand, to make you guys understand. But anyways, so the final idea is we will iterate on the max edge length of the graph. Yeah, and then we will try to maximize the minimum element so that we can maximize the diameter, right? And then we will take the maximum possible value that we get. Yeah, so yeah, this is the solution. But there is a bit of casework involved here, and the code also is a bit complicated. So let's look at the various cases that can occur. So what we'll iterate on is we will try to make the ith element as the max edge weight. If you notice, the weight of any edge is nothing but the minimum element in L to R. So the max edge weight will be nothing but some element in the array, right? So we'll try to make the ith element as the max edge weight. So yeah, Now for the ith element to be the max edge weight, either I minus 1 and I should form a valid edge, or I plus 1 and I should form a valid edge. So either ai minus 1 and ai, so either edge between them. So either the edge between I minus 1 and I should have weight of ai, or the edge between I and I plus 1 should have a weight of ai, right? So this is a necessary condition for the ith element to be the max edge weight, right? So this is the necessary and only condition that we want to satisfy. So yeah, now let's say we try to pair I and I plus 1, and then we will apply the similar casework with I and I minus 1. So we try to pair I with I plus 1. So the first case, so let's see what will be the case when this I and I plus 1, the edge between I and I plus 1 will have a length of ai. So as you can see, the edge between al and ar is nothing but minimum of al to ar. So that means that minimum of ai and ai plus 1 should be equal to ai. So the condition is that ai should be less than or equal to ai plus 1. If this condition is true, then the condition is already satisfied. We don't need to change anything. Otherwise we have to change ai plus 1, and we can convert ai plus 1 to 10 raised to the power 9. So let's look at the first case. So the first case is that we don't change ai, right? Instead of changing ai plus 1, we can also change ai, right? So we don't change ai at all. So this is the first case, and the case 2 will be we change ai to 10 raised to the power 9. So yeah, these are the two cases. Cool. So now what we want is, we want ai to be less than or equal to ai plus 1. So here, if ai is greater than ai plus 1, then we will need one more operation to change ai plus 1 to 10 raised to the power 9, right? So then we need one operation to change ai plus 1 to 10 raised to the power 9. Otherwise we don't need any other operations. So the operations that we have remaining is nothing but either k or k minus 1, depending upon whether ai is greater than ai plus 1 or not. If ai is less than equal to ai plus 1, then we will have all the k elements remaining, all the k operations remaining with us. Otherwise we will spend one operation to change ai plus 1 to 10 raised to the power 9, and then we will have k minus 1 operations remaining with us. Cool. So then what we'll do is, we'll try to maximize the minimum element. So for that, what we'll do is, we'll change the k smallest element. So we will change the rem smallest elements of the array to 10 raised to the power 9. So that's the idea. So yeah, so we will change the rem smallest elements of the array other than I and I plus 1, obviously, because we have already done the operation that we wanted to do with I plus 1, right? Yeah, so that's the idea. We'll basically change the rem smallest elements of the array other than I and I plus 1, and we'll change them to 10 raised to the power 9, and then we'll try to find the smallest element. So then we find the smallest element. So this smallest element can be found out using various methods, but what I did is, I found it using an ordered set. So I put all of them in an ordered set, and then I removed ai and ai plus 1 from it, and then I from the ordered set I found the kth smallest element, right? So then we find the smallest element. Let it be max min. So this is the maximum possible value of the smallest element. So the current answer that we'll get here is nothing but minimum of 2 into max min. So it will be minimum of 2 into max min, or it would be ai, right? So yeah, this way we can do stuff. So this is case 1. But case 2 is when we will convert ai to 10 raised to the power 9. So this is pretty much similar to the first case, but here the only thing is that we necessarily need to convert ai plus 1 to 10 raised to the power 9 as well. So the remaining operations here will always be k minus 2, and we can do this only if k is greater than or equals to 2. So here k will remaining will be k minus 2, and then we'll do the exact same thing. We'll remove the first rem elements from the ordered set, and then we'll find the minimum element of the ordered set, and then the current answer that would give us would be 2 into maxmin and ai then would be nothing but 10 raised to the power 9, right? So yeah, so this is how we handle stuff. If we pair I and I plus 1, we can similarly also pair I and I minus 1, and that would be the exact same thing, right? So yeah, makes sense. So yeah, this completes the solution to problem D. I think it's a bit involved, and it might be a little bit difficult to understand, but nevertheless, if you are still not able to understand, I would suggest you to just watch it again and try to understand what I'm talking about, right? So yeah, this completes the solution. Let's just have a look at the code now. So the code is a bit complicated, so I'll just give a brief overview. So what I'm doing is I'm first of all inserting all the elements in my ordered set, and then I'll just talk about this first case when I'm pairing I and I plus 1. So let's talk about this second case. So here what I do is I just check if ai plus 1 is less than ai or not, and depending upon that I calculate the remaining number of operations that I have, and then I try to maximize the minimum element, and then the answer that I'll get is nothing but minimum of ai and 2 into maxmin. And then the second case is that I convert ai to 10 raised to the power 9. In this case, the remaining operations will always be k minus 2, and then I do the exact same thing, and then I just maximize my answer, right? So I keep doing this by pairing I with I plus 1 and pairing I with I minus 1, and so on. So yeah, this completes the solution to problem D. So yeah, that's all I had planned for today. Thank you so much for watching, and I will see you in the next one.